Now that we've seen basic logic gates, let's talk about a very important property called De Morgan's law. What De Morgan's law allows us to do is to convert from and to or from or to and, with some help from not. Let's look at an AND gate where we invert the inputs and the output. It's a two-input AND gate, so I have two inputs. Let's call them A and B. Now, what do we have here at the output? Well, first of all, we've inverted both of our inputs, so we have not A and not B. We've ANDed those. We have an AND gate here, so we have an AND. And then finally, we've inverted the output. So let's put a bar over that. Now, let's draw a truth table, starting with A and B, and derive this output. So we start with A and B. And we're going to have lots of columns here. First of all, we have 4 possible values of A and B. Let's write those down. Now, the first thing that we do is we invert A and B. Let's do that. We have not A and not B. So here we'll invert A, so we get 1, 1, 0, 0. Here we're going to invert B, so we get 1, 0, 1, 0. Now the next thing we're going to do is an AND. Let's AND these. So we have not A, not B, and we're ANDing them. So we can look at these and we can form the AND. So here we have 1 and 1, so that's a 1. In the remaining rows we have at least 1 0, so these are going to be 0. Now the final thing that we do is we invert this result. So let's do that. So this is going to be not A and not B, and the whole thing inverted. So we can take this and just invert them. So we get 0, 1, 1, 1. So what do we have here? This is our final output. We've had an AND. We've inverted the inputs and the output. And what do we end up with? Well, this is an OR. So you can take an AND gate and you can invert the inputs and the outputs, and then you end up with an OR. And you can do the same thing starting with an OR gate. So you can take an OR gate and you convert the inputs and the output. And if you do the same exercise here, you'll find that you end up with an AND. So De Morgan allows us to convert to start with one gate, like an AND or an OR, and using inversion of the inputs and outputs to convert to the other type of gate. Now we can do lots of different transformations of different gates using De Morgan. So let's do a few of those. So first, let's write down the two that we know. We have an AND gate with the inputs and the output inverted, and we said that's the same as an OR gate. And then we can take an OR, and we can invert the inputs and the output, and we say that that is an AND. Okay, so we're starting from these. Now, let's take this gate. We have an AND, and we put a bubble on the output, so you can think of this as an inverter, so inverting the output of an AND. Well, this has a special name called a NAND gate. And you can see where the name derives because we have an AND followed by NOT. So this is a NAND gate. Now, what is the equivalent OR function of this NAND gate? Well, we can look down here. Here's an AND gate. And this would be the equivalent in the OR of an AND gate. But we have something a little bit different, so we have this inverter here. So first of all, let's start with an OR. And let's invert the inputs and the outputs. So we're taking the AND part of this, and we're creating an equivalent OR gate. But we have this bubble here, this additional inverter, so we need to do this to get the equivalent of this NAND gate. Now, what you should be able to see is these two inverters cancel each other. So if I take a 0 and I invert it to a 1 and then I invert it again, I get a 0 again. So we can just throw these away, and what we get instead is an OR gate with just the inputs inverted, but not the output. So this is a NAND. This is how we can draw a NAND. But we can also draw a NAND like this, as an OR gate with the inputs inverted. We have another special type of gate called a NOR. And you can see why it has the name. We have an OR with a NOT after it. Let's look at the equivalent AND gate for this. So we know from an OR, okay, if we have just an OR, then we can have an AND with the inputs and outputs inverted. So let's do that. So we get the OR part here by inverting the inputs and output of an AND. But again, we have this extra bubble here. So we have to do this at an inverter to get the equivalent function. But just like in this case, these two inversions cancel each other. So a NOR is equivalent to an AND with just the inputs inverted. So we can form a NAND by taking an AND gate with an inversion, as you would normally think about it, an AND with a NOT. Or you can do it this way. You have an OR with the inputs inverted. And if we have a NOR gate, it can be represented this way, or it can be represented this way. These are both the same thing.